All right, so here at first we're going to begin with a quick presentation of the problem. This is a map from Neighborhood Nexus um, of Atlanta. I've labeled here the perimeter, which is this road around the outside, I-75, which is this road right here, and I-20 is this road right here. That makes this the west side. Um, Areas of bright red have an income of 30% below the state average income. The dark red areas are the second poorest in the state, and the purple areas are the poorest in the state. If we look here, we've got a picture of food deserts in the west side. Here's 75 again, 285, and 20. So food deserts are places where people have to go more than a mile to get food. You'll notice that this section right here is these are actually an area of railroad tracks, or kind of a railroad station. So there's a lot right here and around this edge. Now, food deserts have been linked with lower third grade reading scores, higher obesity rates, lower school attendance, lower socioeconomic status, and so addressing food deserts is kind of a step in addressing some of those issues. They can provide vocational training, healthier diets, better fine motor skills for children, and exposure to green space can also has been shown to improve science test scores. So we're actually going to examine the green space using ArcGIS and just the raster calculator to find NDVI and tassel cap greenness indexes. So I've got my Landsat image here, and it's pretty big. So I found the area that is Atlanta by using the footprint on the USGS Explorer website, and went ahead and labeled those things by going to insert text, so that they're easier to find and work with. Kind of created a boundary there. And the first thing I have to do is I have to go to my metadata file, and I'm going to find the reflectance multiplication band and reflectance add band. It's the same for all the bands. So we're going to go ahead and calculate the reflectance from the satellite image. We're going to go to our raster calculator, and we're just going to take that first number from the multiplication band, this one right here, and we are going to multiply that by the band. So we're going to do band 4. You need to put parentheses around that. Double close those, and then we're going to add the add band and come up with an output name there. So my output band name there was reflectance 4 and reflect 5. So I did that for both of those. I'm going to go ahead and turn off some of those layers. And now we need to calculate for the sun elevation. Correct up for that. So if we come up here, we'll find the sun elevation at this number here. I'm going to go ahead and copy that. And we're going to go back to our raster calculator. And we're going to take what we just, the reflect values we just figured out, go ahead and put those in parentheses. And we're going to divide by the sine of that elevation. Okay, and that's going to correct for our sun elevation. And we'll generate two of those. I believe mine are called sun 4 and sun 5. They are right there. I'm going to go ahead and correct up for those. So the bands aren't terribly different just yet. But now we've got our corrected bands, and band 5 is in the near infrared spectrum in a Landsat 8 image, and band 4 is in the visible spectrum. And the normalized differential vegetation index is band 5 minus band 4, or near infrared minus visible, divided by both those added together. So do the same thing we've been doing. We just go to the raster calculator, and we can just take those corrected images of sun 4 and sun 5, and we can just plug that math equation right in there. It'll look like that, and then save our output as our NDVI. So, and then it's going to come out in a grayscale, much like a lot of these. So what I did there to make this a little easier to see is I went to properties, and I just changed my color ramp in the symbology here. I just picked a different one of those. I picked one with two vastly different colors at both ends, and your NDVI value is from -1 to 1. Should always be between those two. And here we'll see a lot of blue up here towards the 1. So there's a ton of blue here. Not so much down here. There's a big group here, a large group here, and some here. This is the West Side Reservoir Quarry. Within the next year or two, this should be the largest park in the city, bigger than Piedmont. It's an abandoned quarry. This is actually kind of an empty area behind a neighborhood here and a neighborhood here. I'm not sure if it's abandoned or city-owned, but it is a rather, if it's not abandoned, then these people right here have some rather large backyards. And this is a park with a school in it. So this is Cary Park, and this is Coretta Scott Land School there. And you'll see these three areas right here kind of address that food desert swath that was here and comes to here, and we still haven't really touched this one. I'm not certain if we will. To get maybe a clear image, we can adjust again with the soil adjusted vegetation index, and all you do for that is the general L value used is 0.5, and it is just the NDVI, except add the L value to the denominator and then multiply the whole expression times 1 plus the L value. So in our calculator, it would look really similar to our last equation with the Sun 5 minus Sun 4 divided by Sun 5. Not trying to have any problems, plus 0.5, and then all of that times 1.5 will give us our soil adjusted. So you'll see that significantly different, significantly less blue there. It adjusted up for a lot of that background radiation, and it leaves our blues kind of just still in those areas. With a lot of this kind of becomes a little less viable. I found some people online that did that without adding it to the denominator and just multiplied it, and you'll see that image is identical. So either way. And then the last thing we're going to do here is I'm going to calculate the tasseled cap greenness index. So I don't have that open here, but I have a chart here that I used from a study I found. And these are tassel cap coefficients for Landsat 8. And so right here's our greenness band. And you see it uses band 2 through 7. So we're going to need to run the same corrections for band 2 through 7 there. And instead of typing all those in and using the raster calculator to do all that, I actually created a model here where I copied the raster calculator and just kind of changed since all my names are very similar, I just changed the 2 to a 3 to a 4. And over here, change the 2 to a 3 to a 4 in the corrected output field there. So it generated all those at once for me. And so now I've got all those up there. And then to get the tasseled cap, what we're going to do is we're going to just multiply those by the coefficients. So multiply by each coefficient. Make sure to put a parentheses around the band, double parentheses at the end, and just add them together. So you'll see those numbers were pulled directly from this line of that table. And then our tasseled cap shows a lot less viable areas. And the blue here goes away some, but it's still denser than some other areas with not near as much yellow. The blue here still exists, and the blue here still exists. So these will be forwarded to the Center for Civic Innovation, and we'll go ahead and compare these to tax maps at a later date with one of our city councilmen that's also a member of the center, and see if we can do anything about maybe the planning of this park, which is in the works right now, the use of this area and the planning of this park, and maybe that school creating some viable green space to serve the community.